we're going to be talking about functions. And in order to talk about functions, we need to define a few things first. So the first thing we're going to define is something called a set. Easier to see right now. Not just bright enough here this morning. Probably a little easier to see, yes? Okay. If ever that situation comes up where I forget to turn the light off or whatever, and you're like, I can't really see very well, just stand up and turn the light off. It's no big deal. Okay? That's certainly an important that you're able to to see what we're doing here. Anyway, so we say a set is a list of mathematical objects where none of those objects are repeated. When we say mathematical object, we mean things like a number, an ordered pair. You could have shapes, etc. In this course, primarily if we're talking about sets, we're going to be talking about sets of numbers or sets of ordered pairs. But a mathematical object's a pretty vague statement. It could include a lot of different things. And we'll talk a little bit about how to represent sets, like the symbols that we use to do this, and some of the different types of sets that we'll talk about, or that we can talk about, and we'll describe how to, write down symbolically those things in a moment. Zach, did you get your one thing? Okay. Can you just drop it off in this pile here? Okay. Thank you, sir. It doesn't have to be neat. So we'll talk a little bit about notation. When I say notation, what I'm really talking about is the symbols that we use to describe these things. Yeah, there's tape at the desk. Again, don't worry about it being the neatest thing in the world. It's okay. You can have some jaggedy edges and none of that's no big deal. As long as it's mostly readable, we're okay. So when we're going to represent a set, typically we represent sets with a capital letter. So maybe I'll use the capital letter A to represent this set. And then to indicate that the list of things that I'm giving is a set, we use like this curly bracket. And I know sometimes that's hard to draw. Just give me an honest effort on that you're trying to draw the symbol. It doesn't, again, have to be the neatest symbol in the world. No worries. And then perhaps we're talking about the set of numbers that are, 3, 4, 5, 6. In which case we can just list those numbers. And then we put another curly bracket at the end. So here we have a set that contains just 4 numbers, right? If you have a set whose list ends, we call that a finite set. The other possibility is you have a set where the list doesn't end. We call that an infinite set. So if I were to make a set that contained the students in this class, is that set finite or infinite? Finite, right? There's, I don't know, 17 or so of you guys. That definitely ends, right? What if I wanted to list all the weights between 100 pounds and 200 pounds? Is that finite or infinite? Finite, okay. So what's the first weight that I would list? Go ahead.
0.031.
Well, 100, right, is what you mean?
Yeah.
Yeah, if we're talking about all the weights between 100 and 200?
Yeah, 100.00.
Okay, and then after that, what would you list? Right, yeah, so that is what I was getting at, right? If the first weight is 100, then I could list 100.1, and then 100.01, and 100.001, and you can see really quickly that there's like an infinite number of weights between 100 and 200 pounds, right? You guys can kind of see that. So that's an example of a set that would be infinite. Since we can't list all of those items because the list goes on forever, we need a different kind of notation to describe an infinite set. Everybody okay with that idea? So let's write an example of what that would look like. So we'll start by giving it that set a name. I'm going to call this the set B. So I'll use the capital letter B. And then I'm still going to use that curly bracket. Now when we describe an infinite set, the way we're going to do this is we're going to say what the objects in the set look like. In this case, if they're the weights between 100 and 200 pounds, those objects just look like a number, right? They're not like an ordered pair or a shape or anything else. So I can just use a variable like x, because all of my items in this set are just like a single number. They don't have like an ordered pair where they have two components to them or something. And then I'm going to draw a vertical line. The way we read this vertical line is we read it as the words such that. Sometimes we might use a colon there. That also kind of means the same thing. A colon being like the two dots, right? Like in English class. You guys remember colons? Okay. I just want to make sure nobody's thinking about like your large intestine when I say colon. And then we're going to have a rule that describes what the things in this set look like. In this case, I'm going to use an inequality. So this is a set of x's where that x is between 100 and 200. Everybody okay with that idea? Now, we should be a little bit careful here. Hopefully you remember from your previous math courses that there's different kinds of numbers. So like there's whole numbers, and there's integers, and there's fractions, and there's real numbers. Right? You guys kind of remember those words, hopefully at least. So here we want to be a little bit careful and make sure we describe what kind of number that x is going to be. In the case, if we're talking about weights, that number could be any decimal, right? Everybody agree with that? If you have a sensitive enough scale, we can measure a weight out as far as we need to on a decimal, right? So what we're going to say here then is that those x's are real numbers. So the symbol we use here is like an E, but it's kind of curvy. and that symbol means is a member of. And then the symbol we use for the real numbers is like an R with a double bar, or a double vertical bar there. And then I'll close my set. And this is an example, again, of an infinite set. So when I see those symbols, what I read is the set B, or B is the set of x's, such that x is between 100 and 200, and x is a real number. Now, as an expectation in this course, I would not expect you to generate one of these infinite sets, like the notation for this on your own. My expectation is if I give you something like this, you could understand what it's saying and give me an example of things from that set, or be able to tell me if I give you a number, if that number is a member of that set. So for this, if I ask for an example of something in this set, you could say 150. Because 150 is a real number between 100 and 200, right? That would be an expectation I would have for you guys. If I said 309, asked you if 319 is a member of this set, you would answer no, because 319 isn't between 100 and 200. Those are the kinds of questions that I expect you to be able to answer, where you understand what the symbols here are saying, but I wouldn't expect you to come up with that string of symbols on your own. Does that seem like a reasonable expectation? Okay. So for this class, would not expect you to be symbol experts, but I would expect you, given us some symbols like this, be able to interpret kind of what they mean and answer questions about what is in this set or not in this set. Okay with that? All right. Hopefully that feels pretty realistic. Okay, so we feel reasonably comfortable kind of about what a set is and kind of how to represent a set. Okay. So the next definition we need to do then is defining something called a relation. So a relation is a set of ordered pairs where the x part of our ordered pair come from some set D. We call that set the domain. And the y's come from some set R. We call that set the range. So let's look at a little bit of notation here. Since a relation is just a kind of a set, a relation could be finite or it could be infinite. So again, because a relation is a set, typically we're going to name that relation with a capital letter, like in this case I'll use the capital letter C. And I'll start with my curly bracket. And maybe my relation is just the ordered pairs 1, 1, 2, 2, 3, 3, and 4, 4. So again, if the relation is just a finite set, I'll just have a list of, some number of ordered pairs. In this case, there were 4 ordered pairs in my relation. Everybody okay with that idea? And again, my expectation would be that you could write finite sets where you're just listing the members. Okay with that idea? But again, relations could also be infinite. So let's do another example there. So I'll call this set D. And I'll start with my curly bracket. In this case, the members of this set are ordered pairs, right? So the things in my set are going to look like X, Y's. And maybe I'm just concerned with maybe this infinite set are going to be things, all the points that look like 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8. All the ordered pairs where the X and Y are the same. Yes, sir. Oh, okay. You're good? Okay. So let's write a rule for that. Well, that rule would be that y equals x, right? That means that both the x and y coordinate are the same. You guys agree there? And then we should say something about what kind of number x and y are. So if we want things that are just whole numbers, like 1, 1, 2, 2, 3, 3, 4, 4, negative 1, 1, negative 2, 2, negative 3, 3, what is the descriptor we call those kind of numbers? Those kind of numbers have a name, right? I thought I heard somebody trying to say it. Integers is correct. So the symbol for the integers is this kind of Z-looking symbol here. This is just the symbol for the integers. We use this symbol that kind of looks like a Z because in German, integer starts with the letter Z. That's why why we're using a Z here rather than an I or something. As most of this notation predates even the formation of America, and a lot of this fundamental mathematics was done, or at least formalized, I should say, kind of in Central Europe. The Germans were often very involved in this. And then we'll just close our set at the end. So if I read this infinite set here, this is a set of x, y's such that y equals x, and those x and y's are integers. So it's going to be just positive, negative, whole numbers, ordered pairs where both the x and y component are the same. Everybody feel okay here? Okay? Next definition. So a function is a relation where every member of the domain is paired with exactly one member of the range. So there's kind of two components to this definition. The first component is that all the things in the domain are used, and the second component is that they only go, or they're only paired with one other thing. Okay. So when we talk about a function and we talk about a relation, which one is there more of? Are there more functions or more relations? Okay, so it says a function is a relation. So let's rephrase this question, ask you something a little bit different. Which one is there more of? Mammals or dogs? There's more mammals, right? Why is there more mammals? Because dogs are mammals. The dogs are a subset of mammals, right? Everybody feels good about that, answering that question. That's pretty obvious. So let's think back to about sets and relations then. It says a function is a relation, just like a dog is a mammal, right? So which one is there more of? Relations. So if we were to imagine if this is all the relations, the functions are contained inside of that, so there has to be more relations than there are functions. Or at least, at best, they're the same size, right? But if you can find one relation that's not a function, you know, there's more relations. Everybody okay with that idea? Okay. So what I want to talk about is some of the different ways that we can represent a relation, and then we'll look at how to tell whether that relation is a function or not, depending on the form. Okay? So the first way that we'll talk about is a mapping diagram. We'll talk about sets of ordered pairs. We'll talk about a graph. And then we'll talk about an equation. So we'll do some examples of what each of these things looks like, and then we'll talk about like what you need to look for in order to determine whether it's a function or not. We'll do some examples of determining whether the relation is a function or not. Okay with that plan? Okay. So the first one we'll talk about is the mapping diagram. So what the mapping diagram looks like is you're going to have two ovals. Typically we label the oval on the left as the domain and the oval on the right as the range. And then we'll list the elements in the domain and range respectively. So let's say the domain contains the numbers 3, -2, 0, and 10. And usually we put a little dot next to these to kind of represent those numbers. And let's say in the range we have the numbers 6, -3, -8, and 13. Now what we'll do is we'll draw an arrow from the domain to the range representing how the numbers are paired together. So maybe 3 pairs with -8, -2 pairs with 6, 0 pairs with 13, and 10 pairs with -3. And I'm just making this up, right? This would be what you'd look at on a problem, is this already put together. So this is what a mapping diagram would look like. What we're going to ask is this mapping diagram that's a relation, is this relation also a function? So if we go back and look at our definition for a function, it says that every member of the domain needs to be used. So let's check that first. I notice that 3 goes somewhere because there's an arrow originating from it. -2 is used. It goes somewhere. There's an arrow originating from that. 0 is used. There's an arrow going from that. And 10 is used. There's an arrow going from that. Those are the only things in my domain. So everything in the domain is used. That part of the definition of a function is satisfied. The second part of the definition is that those members of the domain are only paired with one other thing. So if I look at 3, that's paired only with -8. -2 is paired only with 6. 0 is paired only with 13. And 10 is paired only with -3. So I know that this relation is also a function. Everybody feel okay there? Let's look at some more examples of this, though. So I'm just going to erase my arrows here and these little circles that I've made. And then I'll draw in arrows in a new color and write our answer in a new color. Just so it's easier on me, so I don't have to redraw this picture 85 times. So if we look at this one, is this a function? No. What's the problem? Great. So we have a member of our domain that's not used. So that's not a function, because 0 doesn't go anywhere. Everybody okay with that idea? Okay. Let's do another. Is this a function? I heard some people say yes, I heard some people say no. So let's kind of go through the definition again, just to see if anybody wants to change their mind, since there's a disagreement amongst us. So first thing we'll check is to make sure all of the things in the domain are used. So we have that, right? They all go somewhere. Everybody agree? Next, we need to make sure that they only go one place. 3 only goes to 6. -2 only goes to 6. 0 goes only to 13. 10 goes only to -8. Is this a function? Yes. Everything in the domain is used, and they only go to one place. Does it matter that some of them go to the same place? No. Does it matter that some of the ranges are not used? No. This one is a function. Again, 3 only goes to 6. -2 only goes to 6. The fact they're both going to 6 does not matter in terms of it being a function or not. Is everybody okay with that idea? Okay. And we'll do one more example. How about this one? Is this a function? No. What's the problem with this one? Perfect. 3 is going to 2 places, right? So because 3 is paired with both 6 and -8, that's the problem. So again, when we're looking at whether something's a function or not, we only need to look at the domain or the x's. And if the x's are used more than once, not a function. If the y's or the range are used more than once, no big deal. That doesn't matter. Okay? We feel pretty good about mapping diagrams? Okay. Should write down our answer here. So let's say we have the set of ordered pairs 1, 1, 2, 1, 3, 1, and 4, 1. Do we know what things are in the domain from the information that we're given? Not really, right? We know that in the domain is 1, 2, 3, and 4, but we don't know like if there was more stuff in there or not, right? So what we'll do on these situations is just assume that we don't have to worry about the is everything in the domain used part, and we're just going to focus on that they're paired with exactly one range. Okay? So if I look at that, is this a function? Do I have each x paired with exactly one y? Yes. Does it matter that the y's are used more than once? No. This guy is a function. What about this? Is this a function? No. Okay, why not? So we have the x-coordinate of 1 that's used more than once. So we have 1 paired with 1 and also 1 paired with 4. That's not a function. So again, I'm only really concerned with the x-coordinate here, and I'm only really looking for repeated x's. The y's repeating doesn't really matter to me. Everybody agree with that? So far, so good? Okay. So hopefully you guys at least recall from geometry that a line is made up of infinitely many points. Do you guys remember that? It was an axiom at the very beginning of geometry. So certainly a graph is a relation, right? It's just an infinite number of ordered pairs. You guys okay with that idea? Okay. So we still need to check the same thing. We need to check to see if there's any x's that are used more than once. What would that look like on a graph if I had x's used more than once? If I had one x that was used more than once, what would that look like? Vertical. Who says that? Excellent. Yeah, that's exactly what it would look like. For example, if I had the point 1, 3 and then 1, 5, it would look like that, right? Where they're just on top of each other. So what we're going to use to check to see if a graph is a function or not is something called the vertical line test. I abbreviate that as VLT. What the vertical line test says is, if I can draw any vertical line that intersects the graph more than once, then that graph does not represent a function. So if I can draw any vertical line that intersects the graph more than once, then that graph is not a function. So if I look at this example here, regardless of where I draw that vertical line, it's only going to intersect the graph one time. Everybody see that? So in this case, we can say that this is a function. Let's look at another couple of examples here to make sure we got the hang of this. Is this a function? The graph of a circle? No, right? There's lots of vertical lines we can draw that would intersect this circle more than once. We need just one such vertical line to demonstrate that it's not a function. To really kind of hammer that point home, suppose we have a line with just one extra point not on there, not on the line, and that's what our graph looks like. Is this a function? No, there is just this one spot that I can draw a vertical line that intersects the graph more than once. That one spot being where the point is. Still makes this not a function. Even though there's only one spot that's a problem, that's enough to say that the whole thing is not a function. Is everybody okay with this idea? This typically tends to be one of the easier ones for students. The visual nature here makes it easy. Almost immediately, once you understand that all we're doing is using this vertical line test, you can look at these and almost immediately tell if it's a function or not without even having to do much. It's a very much a I can do it in my head kind of problem, right? Okay. The last one is an equation. So let's say we have the equation y equals 3x plus 5. Is this a function? Bless you. What do you guys think? Is this a function? Okay, you say yes. Why do you say yes? Go ahead.
Because you graph it with a line.
Yeah, so what Lee is saying is the graph of this is just a line. Does this line, or the graph that we've turned this into, pass a vertical line test? Sure does. So we can say this is a function. the idea of taking the equation and transforming it into a graph and using the graph to determine whether it's a function or not is an excellent method to deal with these equation situations. Hopefully, just looking at the form of this equation, this looks like y equals mx plus b, right? Hopefully we all saw that, or at least now that I pointed out to you, you're like, oh yeah, that's definitely what that is. And we know that the graph of all the things that look like y equals mx plus b are just lines, right? So as long as it's not a vertical line, it's going to be a function. And we know that this one is not a vertical line because, well, the slope is defined. Everybody okay with that idea? Okay. Let's look at another example. How about x squared plus y squared equals 4? Is this a function? Okay, so no, why not, Lee? Do you remember what the graph of this is going to look like? What is the graph of this? Not quite. This is so. Yeah, it's not going to go through the origin. But this is a graph that you, or an equation you should recognize from geometry last year. With that as a hint, does that help jog anyone's memory? So it looks a little like the Pythagorean theorem. That's true. But what is the graph of this going to look like? It's not going to be a triangle, although knowing that it's kind of related to the Pythagorean theorem, it's tempted to think that. And it's not a bad guess. The graph of this is a circle. X squared plus y squared equals r squared is the general form equation for a circle. Maybe you remember that from geometry last year. I know that was a long time ago. If I knew that the graph of this was a circle, I would know that this is a function or not a function. Not a function. Now, if you didn't remember that the graph of this is a circle, what I would try to do is see if there's a way to use the same x but get two different y's. So I'm going to make like a little xy table over here and pick an x. Somebody pick an x. 1, I heard somebody say. That's a good one. All right. So if I plug 1 in for x, I have this, right? 1 squared is just 1. And then if I subtract 1 from both sides, I get 3. And then to get the y by itself, how do I get rid of the square down there? Square root. Now when I square root both sides of an equation like this, what do I have to remember to do? Probably many of us forget to do this when we're solving an equation. We have to square root both sides, but there's something that happens when we square root both sides of an equation that's really important. We get a plus or minus. And the square root of 3 is about 1.7. I'll just write 1.7 here. So what I have is two different values for x. You guys see that? Where x, if x is 1, y could be positive the square root of 3 or negative the square root of 3. You could use that as justification to show that this is not a function. If we tried to do the same thing in the previous problem, for example, if I picked x to be 1, I just get one answer, which is a good indication there that what you're looking at is probably a function. So even if you don't remember what the shapes of these graphs are, you can just try plugging in the x's and seeing if, when you find the y, if you get more than one answer, which is also perfectly reasonable. It's a little bit more algebraic approach rather than a like geometric or graphical approach, but it's equally as valid. It's probably no more time consuming. And if that feels easier to you, you can certainly do that. One explanation is not any better than the other. Okay. Let's actually stop here. This is probably good.